Okay, so we're going to go through an example of surface integral, and these can be kind of a pain in the ass. For this one, I have a surface S that's the boundary of a solid half cylinder. So first I need to figure out what the hell this thing looks like, and then I'm going to have to parameterize all the pieces that make up this boundary. So the first thing I'm noticing when I see this thing is I'm noticing that this part here means that I'm above the let's see, I guess that's positive C's, right? So I've got to be above that XY plane. This bit says I'm below, oh, that's where the half cylinder is, because that shape is kind of Z squared plus Y squared is equal to 1-ish, right? It's really actually only the top half of that thing. So what's going on is I've got a shape here. Oops, that's kind of shit. Come on, Joe. So I've got a shape, and this looks like a Quonset hut. You know what a Quonset hut is? It's like kind of funny buildings that you see in ag a lot or on military bases because they're cheap as heck. So it's a half a cylinder, right? Toilet paper tube. Oh, and I cut the ends. Sorry, I didn't say why I cut the ends. I cut the ends with the plane x equals 0 and the plane x equals 2. Hope that makes sense. So that's kind of cutting this thing off. Okay. Now I guess I'm gonna need to name these pieces. So let me put my axes in here. So my axes look like this. So I've got an axis that runs straight down the center. I've got one that runs kind of off on the end and one that runs up. So that's the z-axis, the y-axis, and the x-axis in order, right? Okay. So I I think I'm gonna call my four things something convenient. I'm gonna call my four things. I'm gonna call this face here right for right hand side. I'm gonna call this one here left for left hand side. I'm gonna call this one here C for cylinder, and I'm gonna call this one under here B for bottom. So I'm gonna have four surfaces that I'm gonna have to parameterize. The thing says that I should use outward orientation. Okay. Some of these are going to be relatively straightforward. Some of them are going to be kind of annoying. Um, I'm going to start with one, and then I'll give you a little free rein to see if you can figure out the others. So I'm going to start with R, right. So I think that right is going to be a function of, I'm kind of inclined to write Y and Z here, but I actually think that that thing being a half a circle is probably better in polar. So I'm going to add some of my thinking here. I'm going to say that I'm going to split this thing up into polar chunks, right? So I've got kind of radially constructed spider web there. That's going to make sense to me here. So I'm going to say that's like, okay, I guess that's like Y and Z are kind of playing the role of X and Y in polar, and X is always equal to 2. So I'm going to say this is a function R, which is a function, sorry, a surface, capital R, which is a function, right, of lowercase r and theta. And I'm going to say that means that the x is 2, the y is r cosine theta, and the z is r sine theta. And I think that my bounds, let's see, there's no x bounds involved. I think that the thetas are going to range from 0 to pi, probably half a circle, right? It's got to be. And the radii are going to range from 0 to 1. We'll have to confirm this suspicion with something. How could I confirm this? Guess I could get Desmos out. Let's get Desmos out. Oh, look, it's Desmos. Crazy. Just appeared. All right, so I'm going to throw in 2 comma. I guess I have to type these in U and V, right? So that's going to be U cosine V and U sine V. Okay, and I think the U's go from 0 to 1 and the angles go from 0 to 2 pi. Oh, not 2 pi, pi. Okay, cool. There's one end of my little hut. Now I need the other end. I think that one's going to be real chill because I think the other end's probably the exact same thing with a 0 in it. And that one again needs to go to pi. Okay, cool. Ends, good. I'm liking where we've got things. So I'm just gonna copy this guy, paste it, and I need to change 2 things. It's not an R, and that's not a 2. So that's a 0, and we called that thing left, I guess. Okay, so that's my first 2. I want you to pause the video here, see if you can figure out C and B on your own. It doesn't do you any good to watch me do math, frankly. Does you a lot of good to try to do math. So see if you can do C and B, come back in a couple of minutes. Give you a clue. B is easy, C is a little more complicated. Neither one is incredibly hard. You can do it. So pause this, come back in a second. Okay, welcome back. So let's tackle B for bottom first. So B is going to just be a function of X and Y. And what do I know about B? Well, I know that Z is 0 there. And I guess I'm just going to make X, X, and Y, Y. Seems chill. And the X's go from 0 to 2. And the Y's go from, oops, not 0. The Y's go from -1 to 1. So let's go grab our Desmos back and see if we can make that make sense. Let's see. So we said X and Y and 0. Oops, except we can't use X and Y. We have to use U and V. Oops. Typing's hard, Joe. And okay. So the X1 ranges from 0 to 2, and the Y1 ranges from -1 to 1. Okay, cool. Now I've got a bottom on my Quonset hut. Nice. Now I need the ceiling. Roof's the hard bit. Always is. So, oh, I should have called it R for roof. Oh, but I called the other thing R for right. Run out of letters so fast these days. All right, so let me see. I think for the cylinder, the radius is always kind of 1. So there's like an angle that brings you to a point on the ceiling and then an X that moves you back and forth out to it. So I think I'm going to say this is a function of X and theta. And X is just X, and Y is cosine theta, and Z is sine theta. And I think on this one, X's are going to range from 0 to 2, and thetas are going to range from 0 to pi, probably. Seems like it drives with what I was doing before. Let's go grab Desmos and see if that works. Let's see, so it should be U cosine V sine V. Oops, all in parentheses. Oh, thanks, Desmos. That's nice. It kind of fills that in. Okay. Hey, that purple thing's looking like it's in the right spot. Let's see. U's need to go from 0 to 2. Right? Got to cover the whole distance. And V's need to go from 0 to pi. Okay, cool. So I got my 4 pieces now. Now comes the work here. The work here is for each of these, I need a normal vector. The good news is some of these are easy. So the right one is going to be something parallel to I, right? Because I need a vector that sticks straight out of this end. So it's going to be something parallel to I. I know you want to put I in here because you probably did the problem with the cube first. Can't put I in here because this is parameterized in R's and thetas, so it's in polar. So my guess is that the thing I'm going to get out of this is going to look like, well, it's going to look like R in that first coordinate, and then 0 and 0, and d theta is going to be what I need at the end there. So I just need to confirm this normal vector is in fact R comma 0 comma 0. So how am I going to do that? Well, I need to take the partials and cross them. So we're going to take the partials here, which are going to be, for organization, let me move this down. I'm just going to grab these guys, copy them. Oops, I didn't get them all. I'm going to grab these fellows here, copy them, I'm going to paste them down, and then I'm going to scoot them apart a little bit. Okay, so for R, so these are for calculating normals. So for R, I'm going to calculate R sub R, right? So the R partial of R. Math again, sorry, the names are terrible here. So the R partial of R is going to give me, about 0. And cosine theta and a sine theta. And R theta is going to be again, a 0. That's nice. And then R cosine's derivative is going to be minus R sine theta. And R sine's derivative is going to be R cosine theta. And then I need to calculate cross product. So I'm going to do this, throw one of these guys, throw an I, J, and a K in here. And I'm going to say that out of this, I'm going to get that R crossed with R theta is going to give me. Okay, so in the first place, I have R cosine squared theta plus R sine squared theta. Okay, cool. That gave me what I wanted. And then I'm going to have minus 0. And then I'm going to have 0. Kick fricking butt. Get R comma 0 comma 0. Perfect. Please note, you need to check whether you crossed those in the right order or not, because you may have taken your partials in the other order, which would be fine, but you'd want to make sure it matches up with our outwardly oriented assumption. That's going to let me sort out left real quick. Left as a function of R and theta. That one's going to give me a normal vector that's going to look like minus R comma 0 comma 0, right? Like, okay, so we're just going to not worry about left because it's going to give us that. Then for B, the bottom, this one's parameterized the easy way. This one has just X's and Y's in it, regular old cylindrical or Cartesian coordinates. And so I just need a normal vector that sticks straight down. Great. I'm going to get out of that minus K. So I'm going to get 0, 0, minus 1. The reason it needs to stick down on that, if we look at our little picture, our little Quonset hut here, in order to be outwardly oriented, we need to stick down the z-axis from the bottom. So that's why I got a minus K there. Oops. That's minus K came along with this guy. Okay. And then out of cylinder, things are going to be more complicated. So I'll need to calculate Rx, which is, I guess, 1 comma 0 comma 0. And I'll need to figure out R theta, which is 0 minus sine theta cosine theta. And then I need to calculate a cross product. Okay, so out of that, I'm going to get a vector. And let's see, the I part of it's going to be 0. And the j part of it is going to be, let's see, I'd get a cosine when I need to make it negative. So I'd have a negative cosine theta. And the k part of it's going to be negative sine theta. And I guess I'm a little concerned about this. This point's back in the y and back in the z. This thing's gonna, I feel like this thing points in. There's a way to figure these out. So let me grab my little Quonset hut here and we'll figure this out. I just need a little screen cap of my Quonset hut. Wait 1 second. Okay, so here's my screen cap of my little Quonset hut. And I want to think about the way things change. So if I change x's, that's going this way, right? And if I change thetas, let's see, I need a color that's going to show up on here. That's kind of this way. And if I take Rx, that's the black, and I cross it with R theta, that's the red. By the right-hand rule, I'd get a vector that points in towards the center of the shape, right? So that's where I'm getting this kind of cross product that fits into the shape, which is not really what I want. I should have crossed them in the other order. It's just kind of dumb. So what I'm going to do is I'm just going to say, what this means is that the vector I was looking for was 0 cosine theta and sine theta. Right, I'm just going to revise my negative sign out of that. Cool. All right, now we've got some integrals to do. So the function I have to integrate is x squared, y squared, z squared. Okay. So these are going to be a little tough, mostly just because I can't see what I wrote before. Let's see. So let's do right first. So I'm going to be double integrating. And I'm integrating x squared, y squared, z squared. I'm not real happy with that, so I'm going to leave myself some space because we might have to revise it. And then we're going to end up dotting with, and when I look at right, it was r comma 0 comma 0. And I had this. Okay, so oops. Oh heck, Joe, your bad handwriting is really screwing you up here. Okay, so that's R. And we have to remember what our normal is. So you can just drop that in here. Okay, and our normal was, R comma 0 comma 0. So I'm going to drop my normal in right here. That's R comma 0 comma 0. I've got a dr and a d theta. I know my bounds. My bounds on r go from 0 to 1. My bounds on theta go from 0 to pi. And then this is the problem. This is supposed to be x squared, y squared, z squared, but none of that makes sense here. So what I have to do is I have to calculate x squared, y squared, z squared at this stuff, right? So I have to take my surface functions and plug them in. So x is 2. So that means I've got a 4 in the first place. Y is r cosine theta. So that means I have an r squared cosine squared theta in my second place. Z is r sine theta. So I have an r squared sine squared theta in my third place. And the nice thing is when I do this dot product, I get the integral from 0 to pi, the integral from 0 to 1 of 4r dr d theta, which is super chill. The d theta's done, just throw a pi. So I get a 4 pi, got the integral from 0 to 1 of r dr. That gives me 4 pi times r squared over 2 evaluated from 0 to 1 gives me 4 pi over 2. Oops, guess we can just call that 2 pi. Nice, check done. Let's do B. Sorry, let's do L. So L of r and theta. I just happen to remember this. We could go look up top if we wanted to. It's 0, comma r cosine theta, comma r sine theta. Bounds are the same, and our normal vector was negative r, comma 0, comma 0. And so my integral is going to be, I'm going to integrate from 0 to pi. I'm going to integrate from 0 to 1. Let's see, I've got 0 in the first place. I've got r squared cosine squared theta and r squared sine squared theta in my second and third places. And then I'm dotting this with minus r 0, 0, dr d theta. And out of that, I'm going to get 0. Why'd I get 0? Yeah, because the dot product's 0. Cool. Those two vectors are perpendicular to one another. Great. What that means is that the flow field isn't flowing through the end of the Kwanzaa dot, right? All the air is moving kind of around in that plane, but none of it's going through. So if you stood in that doorway, there might be a breeze, but it's not in your face or at your back. It's just kind of across your, like, it's not in your face, right? It's not coming at your face, it's across it. Okay, cool. Guess I got to do bottom. So bottom was a function of x and y. And I guess that one was x and y and 0. And the bounds were from 0 smaller than x smaller than 2, and y's were from negative 1 to 1. And my normal vector was 0, 0, 1, I think. Okay, so now I need to integrate from minus 1 to 1, integrate from 0 to 2. I've got my function, which is x squared, y squared, and 0 squared. Right, so I took these x, y, and 0 and plugged them into my vector field. Now I'm dotting with my normal vector, which is 0, 0, and 1. And I would be integrating dx, dy. Good news is this is 0 anyways. Neat. Chill. Good. I'm gonna go collect the cylinder because I don't remember that one off the top of my head. And we need to remember it's 0 cosine sine. Okay, so cylinder normal vector is 0 cosine theta, comma sine theta. Okay, cool. All right, so now I'm going to integrate. I'm integrating from 0 to 2. I'm integrating from 0 to pi. I just nailed down that those are d theta dx, and I don't want to forget it. I guess I'm integrating x squared, comma cosine squared theta, comma sine squared theta, dotted with 0 cosine theta sine theta. Okay. Well, that's probably not super convenient. So I've got integrate from 0 to 2, integrate from 0 to pi. Well, I guess I get cosine cubed theta plus sine cubed theta d theta dx. That's kind of annoying. Well, I guess we're gonna have to do some integration. The good news is the x integral just throws a 2, so we can reverse the order and just integrate dx first. So I've got a 2, and then I've got times the integral from 0 to pi. Let's see. I think I remember that the way you integrate cosine cubed is you take one of them and turn it into a 1 minus sine squared or something. I'm using cosine squared plus sine squared is 1, the Pythagorean identity, and rearranging it a little bit. So I've got a cosine theta times a 1 minus sine squared theta plus a sine theta times a 1 minus cosine squared theta. Probably a better way to do this. Probably some sum of cubes identity or some nonsense, but this will work. Let's see. So I got a 2. And now I've got an integral from 0 to pi of cosine theta. I'm going to split all these up so I can do them individually because I don't want to mess around with this too much. D theta minus the integral from 0 to pi of cosine theta sine squared theta d theta plus the integral from 0 to pi of sine theta d theta plus the, oops, not plus, minus the integral from 0 to pi of sine theta cosine squared theta d theta. Okay. Couple of these, one of these I can sort right now. Integrating from 0 to pi cosine is an up half bubble and a down half bubble, right? That's this. Oops, that was a trash picture, Joe. So cosine's one of these guys. 0's here, pi is here. That guy and that guy cancel. I get a big old fat 0 out of this. You do the same trick with this one with the sine, except those are both up. So I get an answer of 2 out of that one. Then for the other two, those are both a u sub. So in this one, I let u be sine theta. Then du is cosine theta, d theta. So I've got that guy. And so in my next stage here, I'm going to get a 2. Let's see, I've already dealt with that one. That's 0. So I've got a 0 minus. I'm going to have an integral. I'm going to get a u squared du out of that thing. And when I plug in 0 and pi, I get integrating from 0 to 0. Oh, hell yeah. That's super convenient. That one zeroes out. Then I'm going to have a plus 2. That's from my sine theta up there. And then I'm going to have a minus, and now I need another u sub. So on this one, we're going to let u be cosine theta. Then du is going to be minus sine theta, d theta. That's nice. Got all of that stuff kicking around, including the minus sign, which is kind of slick. So this is then going to be plus. Going to be integrating. We're going to be integrating u squared du. And when I plug in 0, cosine at 0 is 1. And cosine at pi is minus 1. Weird. Okay. Okay, cool. So I guess out of that I get something. Let's see. So all told here, I've got 4 plus 2 times u cubed over 3 evaluated from 1 to minus 1. That's kind of inconvenient. You might remember you could swap those and put a negative sign up front, or you can just remember how it works. So that's 4 plus 2 times -1 cubed over 3 minus 1 cubed over 3. Let's see. And so I think that's 4 plus, I guess that's 4 minus, obviously. And that's 2/3 in there, and really minus 2/3. So I'm going to get minus 4/3 here. Oops, not the answer to the problem. Which is, let's see, 12 thirds minus 4 thirds. Give me a total of 8 thirds out of that one. Okay, and then there's 4 of these that I have to add up. So a double integral over the surface of f ds is, let's see, first one I got 2 pi, second one I got 0, third one I got 0, and fourth one I got 8 thirds. So I got 2 pi plus 0 plus 0 plus 8 thirds is 2 pi plus 8 thirds. Am I concerned because that's an ugly number? Yes, I am. Am I done with this problem? Probably. So, yeah, that's what there is. Break it into the pieces, deal with the pieces individually, make sure they're oriented in the right directions, make sure you get your normal vectors right. It's kind of tedious. There's a reason we taught you, there's a reason I assigned you this horrible problem, and it's not just to torture you, it's to make you appreciate your life. It's really just because we're going to get a tool, and I kind of need to show you that it could suck without the tool so that you'll appreciate the tool when you have it. Sorry, my bad.